we extend a hearty welcome and sincere gratitude to the resource speaker, Shri Vivek Kapadia, and also convey our sincere thanks to all professionals for their time and presence in the virtual training on the topic on use of geosynthetics in rock engineering projects, seepage control in underground structures and tunnels. Now I invite Professor Mahinder Singh, President ISRM India, for the opening remarks.
Thank you very much. At the outset, very warm welcome, Mr. Vivek Kapadia ji, and also on behalf of the ISRM India, I welcome all the participants who are here. We are going to have a wonderful lecture today. And as we know that these days there are a lot of infrastructural developmental activities are going on and a lot of tunneling projects are going on. And the field of rock mechanics is having more and more importance. Can I, there is some noise.
Can I request to the participant kindly mute their microphone, please?
Dr. Sanjay. So friends, yeah, I was talking about that rock mechanics has assumed so much of importance these days because of the projects which are being undertaken at our national level as well as at international level. And especially when you talk of the tunneling projects, then there are a lot of stringent requirements which we have to follow. So the International Society of Rock Mechanics, to which we are a part, it was established. I just want to give small introduction to that without taking much time. So ISRM was formed in the year 1962 in Salzburg, and there were some catastrophic events which made a pathway for this particular society. And since then, it has been working for the promotion of the activities like collaboration of exchange of ideas, encouraging teaching, research, and advancement in the knowledge of rock mechanics, and also to hold conferences, seminars, etc. Our group is one of the 60 national groups. So ours is Indian National Group of ISRM. And we are actively involved in these activities. And one of these activities is today, for which we are thankful to Shri Vivek Kapadia ji. And I would also like to inform you that ISRM holds international symposia, and you will be happy to know that 13th Asian Rock Mechanics Symposium, which is a very prestigious event. And after a lot of efforts, we have backed that. We have been selected for this particular Asian Rock Mechanics Symposium, and we will be having it in the September 2024, so 2.5 years from now. So I hope that many of you will be joining us in that event. From the ISRM India, I would also like to request you that you should go through our journal. ISRM India journal is there, and my request is that you should please send as many articles as possible, whatever work you people are doing. Especially field-related work is rarely available, means in the academic journals, and our aim is to promote the field activities and to get more insight into the field, because academics generally we lack in that. So in all the journals you get the academic things, but field related articles are most welcome, including the academic ones. With this brief review about the ISRM, now it is my pleasure also, if I am permitted, to introduce our honorable speaker today, Shri Vivek Kapadia ji. He is at present Secretary to the Government of Gujarat, and posted as Director to the Sardar Sarovar Narmada Nigam Limited. And he has obtained Masters in Engineering, law, computer applications, and management. So a wide experience you will see from his lecture also. And he is the Vice President of the Central Board of Irrigation and Power, Government of India, and also the President of International Geosynthetics Society, India. And he has been in this field of water resources engineering and management for last more than about 24 years. And his focus areas are design, execution, and repairs of large irrigation projects and policy making. So you can see he is involved in policy, not only in policy making, Mr. Patel was telling me, but also in executing those ideas in the field. And he was one of the pioneers of participatory water conservation movement in Gujarat, and has done extensive work in rejuvenation of ancient Indian water conservation systems. So that speaks of his very variety of the work. And he has an extensive experience in application of geosynthetics in civil engineering. So with these few words, now I would welcome our honorable speaker to go ahead with the lecture, Use of Geosynthetics in Rock Engineering Projects, Seepage Control in Underground Structures and Tunnels. We know this aspect is very, very important, especially for our construction engineers. We welcome you, sir. Please.
Thank you so much, Professor Singh, for beautiful words for me. I have shared my screen. May I know, please, whether it is rendering okay to everybody?
We are not able to see it at the moment.
Okay. Is it now rendering?
No, I think you can unshare and share again.
Okay, okay, okay.
Otherwise, you log out and log in means once again. So sometimes it works.
Is it? Okay, just a moment.
Sorry for these hitches. Means these types of the things are now common. Everything works smoothly. Sometimes there are some problems, and we are sorry for the inconvenience.
Is it all right at the other end?
Still, we are not able to see your screen.
No, sir, we are not able to see.
Is it okay?
No.
Or still not visible?
No.
Still not visible.
Still not visible. My open share tray option is not working. May I please know whether this privilege is given to me?
Can I request CBIP IT team to help us out?
This facility is available with you, sir. We make you
actually,
as a presenter.
Open share, I'm clicking, and this is the screen sharing that I'm going to.
You try
window entire screen I'm sharing, and
yes, sir. Now
this is working.
Yes, sir. Yes. Sir.
Okay, so may I go to the full screen mode and?
No, still your.
Yet PPT is not visible, sir. Yes, now.
Is it okay?
Yes, sir.
Shall I go through the slides?
Yes, sir.
Slides are not visible.
Slides are not visible.
It's visible now. Okay.
Is it okay?
Yeah.
And this is my full screen mode. And the entire topic that has been given to me is very vast, though I am not an authentic speaker on the tunnel engineering. Especially, I am a structural engineer with special experience to application of the geosynthetics, but I have done some work in tunneling, and that's why I will be able to share some of my experiences with you. So in the underground structures, the common beliefs, they are like this. underground structures are safe against earthquakes. Another belief that we are subscribing to is underground structures deform with supporting surrounding ground. And the third belief is that deep structures are safer than shallow structures. All these misbeliefs, they are actually emerging out of our codal provisions. Some of our Indian codes provide that the buried structures are not required to be analyzed by dynamic methods. And these kind of provisions give us a wrong impressions. And that's why these beliefs are nurtured in the society. But actually speaking, the spirit of the code, when it says that dynamic analysis is not needed, they want to say that either you go for the finite element analysis or you go for some pseudo-static analysis. They will better work for the underground structure. That is the spirit of the IS code, but we don't take it the right way. So here I am taking you about the journey of the earthquake and their effects on the surface structures and the underground structures. The differences are very starking on the structures lying on the surface of the earth and those which are buried in the surface of the earth. So the phenomenon is that the soil surface vibrates and structure oscillates, causing inertial forces. This is the net effect of the earthquake on the surface-based structures. Whereas if the same structure is underground, then seismic waves propagating in the medium induce drifts in the structure. So these are the two differences, especially. Then lower point of view, the load induced by seismic forces that is proportional to the acceleration, whereas the load introduced by seismic strain is proportional to the velocity. This, I think, is the most critical difference between the two. Here on the surface, when the structure is lying, it is the acceleration-based analysis. And when it is underground, it is the velocity-based analysis. So this is the fundamental difference from analysis point of view. And that's why the IS code says that when the structure is buried, better you go for the pseudo-static methods or pseudo-dynamic methods. Interaction point of view, the common problem is possible to neglect the soil structure interaction for the structure resting on the ground, whereas it's not possible to neglect the soil structure interaction when the structure is underground. The analysis point of view, in the common problems, linear analysis is possible when it is on the ground, whereas this highly nonlinear approach that is required in the buried structures or the underground structures. And that's why, because of the non-linearity that the code provides, that better we go for the pseudo-dynamic or pseudo-static kind of an analysis. So this is the most important thing that we need to understand. So this is something, what you can say, disillusionment at the very outset that I was supposed to do. If we understand the first category of the structure that is resting on the ground, rockfill dams and canals, these are made up of the rocks. Let us start with the first set of the slides over here. The geosynthetic membrane, how it is used in the rockfill dams. Usually in the rockfill structures, you know that the most critical aspect is the seepage. What kind of seepage path that you permit, and accordingly you design the base width of the rockfill dam. But we try our level best to see that the reservoir side has some kind of sheath or impervious layer. In the olden days, it was the concrete slab that was put in on the face of the rockfill dam. Even the dry masonry was also done sometime, but now we have replaced them completely, and we provide a geosynthetic membrane on the upstream face or the reservoir face. The same way in the foundation, if imperviousness was required to be provided, we nowadays prefer the basal reinforcement come geo reinforcement at the ground. And that is how we ensure that permeability is within the control or within the acceptability limit. This is a rockfill dam of Italy that I have provided over here the picture of. The geosynthetic membrane, how it was provided in, can be seen over here. The geosynthetic sheet has been covered with the concrete slab. So the reason is geosynthetic material is not very strong in the UV exposure, and that's why it was required to be covered. But the basic impermeability has been attained by the geosynthetic sheet. Actually speaking, in the olden days, the same material that was used was the bituminous sheet. And nowadays, we go for the polysobutylene kind of a sheet. Now, even the HDP is also practiced for the smaller dams, and for the bigger dams, we use the PVCP kind of a material. But that is very effective. In the Rockville Dam, if we require to provide the filter, we go for the geosynthetic material nowadays. In the olden days, the practice was to go for some kind of granular material, like the the gritty material or the pebbles and so on. But now we go for the geosynthetic filter. This is the Hans Strijdom Dam of the South Africa, in which it was PET kind of a geotextile filter. And in the geotextile filters, both the functions can be attained, filtration as well as drainage. And that's why this dam is standing since years together. So it is a time-tested project with the application of geosynthetics in the Rockville Dam. Then I'm showing you here a dam of the Australia. Again, you can see here the steel reinforcements are provided uh, in the downstream side. That is something, very special kind of a mechanism that you can see over here. Usually it happens that in the Rockville Dam, only the mechanical bonding of the rocks or interlocking that plays a vital role in the stability. But here they have gone for the reinforcements. How it comes? How the stability will be attained by providing the geo reinforcements. Actually speaking, the rock material is interlocked into the biaxial geonet or the steel mesh, and that is how tension is attained into the steel mesh or the biaxial geogrid. And that is how we ensure the stability of the downstream side. Then what is the net advantage? I shall take you to the next advantage in the subsequent slide, when I shall show you the earthquake resistant design of the structure is actually speaking ensured with this kind of geo reinforcement mechanism. The sites which are susceptible to high magnitude earthquake or low magnitude frequent earthquakes, then the Rockville dams are extremely vulnerable. In that kind of situation, these kind of reinforcements, be it of steel or polypropylene, they are widely used. Even nowadays, the polyester geogrids are also available that can be used in these kind of structures. I am to take you to a Rockville Canal here. This is my own experience. You can see here that this Rockville Canal, this entire Rockville Canal is abutting a mountain. And the material was taken from the same mountain. It is high bank canal, and it carries water inside. And this is a significant discharge carried by this canal. It is somewhat 35 cubic meter per second discharge. It is very big. Over a period of time, we observed that this entire Rockville mass, that is the canal, that started developing voids inside, and that's why there was a big outflow over here. It was to the tune of 357 liters per second in a 100-meter stretch. So it was profuse percolation from the voids within the rock mass. So we went for a geophysical testing. We found the water paths, and accordingly we chalked out our strategy. We simply put a geomembrane on the surface of the existing canal, and we put another layer of lining like this, and that is how we ensure that it was completely seepage free canal. Otherwise, it was a huge wastage of the water, and moreover, the stability of this outer slope that was also endangered because of the path of the water developed within the embankment of the rock mass. So this is how the geosynthetic membranes work. Now I am taking you to the underground structures. Up till now, the discussion was focused on the structures above the soil mass or the ground. Underground structures are susceptible to high magnitude of deformations, and serviceability is a major concern in the underground structures. I'm taking you to the crux of this matter. Suppose we have laid a buried service line. Maybe it is a drainage line or a crude line or a gas line or whatsoever. But the mass above this pipeline, that is the soil mass or the rock mass, whatsoever the case be, you know, this pipe is extremely dangerous. When the load comes from the top, either vehicular load or any kind of punching load or so, then this pipe becomes extremely vulnerable if this soil mass is unable to take sufficient load and it simply succumbs to the load. In case it settles too much, then the pipe either cracks or it undergoes some kind of ovaling deformation. So this is very dangerous kind of a scenario. So we put the multiple layer of geosynthetic like these, and we reinforce the soil mass, and we ensure the performance and the serviceability of this kind of buried pipeline. And there are so many case studies that you can see nowadays in which the buried structure is protected by way of geo reinforcements on the soil at all. I can show you one practical example in which the geosynthetic material was utilized to protect the serviceability and the safety of these kind of conduits. One layer of geosynthetic was simply laid over that in one case. In the same pipeline, there were two layers of geosynthetics applied to understand how the behavior is improved by multiple layer geosynthetics. It was biaxial geogrid that was laid, and the conclusion was there was a minor reduction of 11% in the settlement in the single layer of the geo reinforcement, whereas in the two layer, it was 38% of the reduction in the subsidence of the top load in the plate settlement. So you can see that it is not simply that you add one more layer and it is multiple reaction, that is geometrically proportionated reaction. The reaction goes, in the power value. So 11% to straight away 38%. If you use the third grid on the soil mass at top, then you will get the reduction of say 56% or so. So that is how you can improve the behavior of the filling material, and that will ensure the proper performance and serviceability of the buried service line. In case you have to work in a waterlogged situation, the groundwater table has come right up to the top of the soil, and you cannot lay the pipeline. Then what nowadays the people do, people simply excavate the trench, lay down a proper geomembrane on the sides of the trench, fill the material with the coarse aggregate like basalt or so, and lay the pipeline inside. And this material, not only from workability within the water presence, but in the behavior point of view, these kind of trenches perform much better than the conventional dewatered trench and pipe laying kind of a situation. So this is the application, practical application of very challenging kind of a project. The cost of the pipe is not material, but the serviceability of the pipe is the real matter. Now, if I take you to the underground frame structure, maybe a metro railway station. If you go to the Madras, there is underground railway station of the metro line, and you can easily see here that the frame structure is looking like this. What kind of forces and equilibrium systems work? This is the foundation reaction, and this is the backfill and traffic load atop it. And here are the live loads. And what you can see here are the sideway reactions on both the sides. Even the moments are also there. This is the equilibrium diagram of this kind of planning, and But anyway, you can see that because of these kind of moments at the ends or the corners, there will be not only the cold joint formation, but there will be, some kind of structural joinery developed over a period of time. This is called long-term plastic joints in the structures. So in order to prevent the leakages from the surrounding soil, we simply wrap these kind of walls with the geomembrane, as I have shown over here with the dotted line, and you can ensure that the performance of the structure or serviceability of the structure would be lifelong by this kind of application of the geomembranes. If you see the frame structure, there are sometimes the challenges in the form of drainages from the outside. The groundwater table is also above. Sometimes the rainfall is so heavy that the water percolating from the ground, that will be haunting the performance of the structure. And that will be also mounting the water pressure from the surrounding. So these kind of water pressure you can see. The arrow I have drawn, I think I should change the color to make it visible. These kind of water pressure, that is called the lateral water pressure, that is developed on the walls of the structure. And these kind of lateral pressure induces tremendous moment on the corners. In order ensure the safety of the structure, we provide a bottom drain like this. These bottom drains are also made up of geosynthetic materials. They are covered pipes. These covering material is the geosynthetic, and that is actually the filter material. And that is how the water is attracted by the drain. The water is not allowed to remain present over here for a long time, and that's why there is no long-term moment induction on the joint of the structure. Sometimes we apply the geosynthetic in the base like these, and we fill up with the gravelly material like this, and we allow the water straight away to go to the ground, and we dispose it somewhere else at the far off point. This is inclined drain, and this is the vertical drain just adjoining the wall, and that is how we protect the underground structures with the help of geosynthetics. And especially in the rocky grounds, these kind of drainage applications are very important. The same way, we use the geosynthetic as the basal reinforcement in the foundation of these kind of frame structures. If the rock mass is not strong enough, or maybe there would be some kind of weak patches within the rock mass, sometimes the shale or the clay layer is confined within the consecutive rock mass, then we have to provide some kind of the basal reinforcement in order to ensure permissible settlement within the limits. So this is the application in the foundation engineering, basal enforcement, and that is how the bridge abutments are made safe. In the ponds are dug up water bodies. Usually, we have developed a perception that geomembranes are used in the ponds to reduce the seepage rate. But another application is that some places where the inherent soil chloride pollutes the water within the water body or the pond by infusing chloride into the water, that is called breakishness intrusion. In these kind of challenging soil, if you want to retain the water for a long time, you can apply the geomembrane in the bottom and sides of the water body. You can store the water for the entire year. On the sea coast of India, there are several locations where brackish water intrusion has been a problem, and we sort out the problem using the geomembrane like this. This is again the application of geosynthetics in the underground structure. Now I'm taking you to a very special application called the landfill application. In the landfill, all the solid waste is required to be buried, and we have to see that this solid waste does not come out either in the contact of air, in the contact of surrounding water, in the contact of soil as well, because this solid waste is extremely dangerous. Sometimes even nuclear waste is to be disposed like these. So there is special design like these, and we use the geosynthetic material to cover it up properly, and they are called the chemical resistant geomembranes, very special geomembranes. But municipal solid waste, even the nuclear solid waste, is disposed like these, and that is the environmental protection system that we design using the geosynthetics. So again, it is an underground application. I am taking you to a very special application called the stone column. You all know that stone columns are used to improve the bearing capacity of the weak soil by giving proper drainage to it. So we dig actually a column, fill up with the stone, and then apply the pressure so that whatever water is there in the soil that is gathered in the stone when the load comes, and this water actually is disposed, and that is how the soil becomes consolidated. So in this kind of application, if we use the geosynthetic encasement with the filter properties properly designed in the stone column, then you will get two advantages. You will get the settlement very fast because you can go for larger diameter of the stone columns. Number two advantage is that these stone will not be mixed with the soil, and that's why its drainage property will be intact. So the performance will also better, and the life of the stone column will also be for long years. And that is how you can ensure a very long-term performance of this stone column, and the foundation behavior will also be uh, very much enhanced by this kind of application of geosynthetics. So this is the soil consolidation or the stone column that we can use for. And now I am taking you to the tunnel, that is the most challenging structure, is the buried structure. You can see here that when there are faults in the rocks or folds in the rock, sometimes the folds are the faults as well, sometimes the folds are merely the folds and they are not the faults. But in any case, the seismic loads on the tunnel lining that will come over here, you will be resorting to different kind of strategies to protect your tunnels. Sometimes, these kind of fault encountered, and you will go for the the rock nailing or the rock bolting like these. Sometime if the rock bolting is to be done in the foundation, you can go for these. Sometime if this kind of situation is there, your 2/3 of the channel comes under the danger, but you simply go for the rock bolt in the top crown, and that is how you design the safety of the channel. But there could be different situation, and according to the waves generated by earthquake on a particular location, if there is a site where the primary waves are predominant in the earthquake, then there will be compression lengthwise in the entire tunnel, and the tension in some part of, but that is basically axial compression and axial tension. But this is basically a product of the primary wave of the quake. If it is shear wave, then obviously there will be an axial bending in the tunnel like these. And if there is some kind of relay wave predominant in the quake, as per your site situation, then there will be some kind of ovaling deformation, and accordingly the shear and bending into your lining of the tunnel. So even there is minor displacement that may cause disruptions in the services. So that is the real matter of concern while we design the tunnels. So what do we do normally? We understand the variations around the tunnel in the rock mass on the short term and long term basis. The variation of the stress field as the face advances away from the point concerned in the tunnel is called the stand-up time, or the short-term variation. And in the long-term variation, we consider the creep, that is under the constant shear stress, sometimes the influence from the environment, durability of the rock mass, and effect of the groundwater. All these are the long-term variations around the tunnels that we need to consider while designing. And this is a classical chart for the sustainability measures for the design of the lining material. In case the engineering rock mass that you classify is 1 2 3 4 5 and all, and you take on the y-axis the equivalent dimensions of the different treatments, then there are different zones: the cast concrete or bolts and fibercrete, and bolts and shotcrete, and pattern bolting and spot bolting. And sometime even you have extremely safe a tunnel, no support is required. So this is how, we simplify the sustainability measures, but we have to take all these measures into consideration while we design the lining of the channel. So usually we understand the deformations in the lining of the channel or the stress response by the lining of the channel in two different ways. If this kind of, the shear failure is there in case of rock burst, this is the rock burst, and you can see that there will be shear failure into the direction perpendicular to your uh, uh, lining sheath. Sometimes, it is called the incipient extension of the rock, and this is called extension strain slabbing of the rock, and these also will be inducing stress into the lining. So how do we tackle them? So we understand the entire behavior of the lining, the response of the lining in these three categories: complete shear failure or buckling failure. Buckling means axial forces on the same axis, and that is mostly the compressive. So the deformation is not within the plane of the forces is called buckling. Then the tensile splitting, that is called shearing and sliding. Like this, the forces are like this, what you can see over here, and this is called the shearing failure. So this also can happen. So these are the main failure modes: the squeezing of the ground, and we design the lining for these three kind of situation. If we take a larger view of this situation, finally you can understand that whatever the movement occurs in the rock mass, that is to be duly taken care of by way of confining that rock mass in the tunnel opening. So what is the confining agent or the confining material? That is your lining itself, your composite lining. That's it. That is the only confining or supporting material to hold the rock mass into its place. So the principle of confinement of the rock support is considered as this, and this is called the overstressed element, for which we design the entire lining, because we don't know as to where the overstressed element will occur. So we design the entire lining for this kind of overstress anywhere in the tunnel section. If we see the the damage behavior or the distress behavior of the tunnel lining, then let us understand how gradually it occurs. Sometimes it happens that the damage is of only level 1, what we call level 1. The first stage is the occurrence of the cracking in the concrete material, and then the bond strength between the steel and the reinforcement and the concrete is reduced gradually, but the steel has not reached yet the yield point. And here is the point where the yield point in the steel has occurred, and the level 1 damage, now that stage is over. Means now whatever damage beyond these will occur will be plastic deformation. So the damage 2 is called the stage of plastic deformation, in which the yield point of the reinforcement has already been crossed, and now the maximum sustainable load takes place somewhere. That is called the ultimate load uh, for the behavior of the composite material like these. And from that point over, whatever load is there, though the load reduces, the plastic behavior continues further. The failure stage has now come. So this is actually speaking a state of distress, may be unrecoverable. And that is how we identify the damage level 1, 2, 3. And for these kind of situations, we design our material, we test our material. So now the geosynthetic, how it is used nowadays. If you see here, this is the rock mass. Say this is the rock mass on the outer side, and this one is the shotcrete or the concrete or the fibercrete, whatever you call it, or you have designed it. Inside it, what we have placed over here is the drainage material. You know that drainage in the geosynthetic terminology means what? It gives way in the plane of the material is called drainage. and when it gives way perpendicular to that plane of material is called filtration. So this is the drainage material, this is geocomposite, what we have applied over here. Then it is covered with the geotextile protection layer. Because this drainage material is required to be protected from both the sides, there is one shield of the geotextile protection. I shall take you to the properties of the geotextile protection. Then this is the fixing mechanism, and then on it is put another geomembrane that is further protection to this geotextile. And then we put some injectioning equipment, and then we put the inner concrete lining. So actually speaking, there are two concrete linings on the outer side, and in between is the sandwiched multi-layer geocomposite. So this is how nowadays the tunnels are designed for the waterproofing and drainage purpose. Why waterproofing? So as to ensure the serviceability of the tunnel, so as to protect your electricity cables inside the tunnels. And why drainage? Because the drainages will facilitate longer life to the rock mass around your tunnel. I shall come in detail in the subsequent slide. This is typically the section of fixation of the geomembranes and geotextile. This is a typical mechanism by which we use this material, duly covered by the shotcrete and the concrete liner inside. And that is how the fastening system takes place for every tunnel, for every lining. We go for designing special kind of joineries and special kinds of materials, the geocomposites, and there could be different variations. But what are the benefits of geosynthetics over here? The first benefit that is that surrounding rock mass does not remain in the contact of water for a long time. And that's why it maintains the mechanical bond within. And that is the most important thing for the stability of the rock mass. The same way, bond between the shotcrete and the rock, that also remains unaffected because there is no water. So the bond between the rock mass and shotcrete, that is again very important to allow the stress interaction between the natural material and our lining material. And the third benefit is that corrosion of the reinforcement within our tunnel liner, that remains far away. So the rate of the corrosion is retarded. And that is how we ensure uh, longevity of our concrete composite lining. So these are the main benefits of application of the geosynthetics, and that's why we widely use now the geosynthetics into our tunnel engineering nowadays. This is my own example. There is, I showed you once the canal, that is the Rockville Canal of the Panam Dam, that was in high embankment, made up of the Rockville itself. And this is the tunnel that is taking, the water from the reservoir to the canal. So this tunnel is a very long one. It is more than 800-meter long a tunnel. And this has also been designed with the same kind of, drainage designs and reinforcement design. I would say that geosynthetic is not actually to enhance the strength of the lining, but it enhances the context in which the strength of the lining remains intact. So these are, very loaded words of mine. So the properties of the geosynthetics for this purpose, that is the lining of the tunnel, the first is the chemical resistance. It is actually to, remain in the contact of the calcium hydroxide in the groundwater, and that's why its design range for the pH value is 2 to 13. Extreme alkaline material, extreme acidic material, both can be resisted by these kind of geomembranes. The same way, the mechanical resistance, it has very high tensile strength and high elongation as well. Why this gives you benefit? In case our tunnel lining has entered damage level 2, then there will be plastic deformation and water will have a through permeation. But this mechanical resistance of the geotextile will not allow it to break, and that's why this will not give way to the water. So our performance and serviceability will remain intact, though we have entered into plastic deformation stage, that is damage 2 of the shotcrete lining or the fibercrete lining. Then the hydraulic transmittivity, the normal compressive loading is say 2 kPa, under which we keep the permeability within the limits of 8 into 10 raised to minus 1 centimeter per second. For the 200 kPa load, that is extremely high load, we can design the material, say 8 into 10 raised to minus 2 centimeter per second kind of permeability, as good as impervious material. The same way, the decay resistance, the contact with the soil and water, which may contain aggressive microorganisms. So there is decay resistance of very high magnitude into these kind of geocomposites, and that's why we use these materials to protect our channel lining. So that is how our entire rock engineering, that is supported with the application of geosynthetics, and that is how we apply the geosynthetics into the rock engineering. So here is the end of my deliberation, and now I think we should open the floor for questionnaire. I think I have taken rightly 32 minutes. I was given 30 minutes only. I'm sorry for 2 minutes of overshooting. Thank you, Professor Singh. Over to you.
Thank you, sir. Thank you for making an excellent detailed presentation. Now I request to the participants, they may ask the questions.
Vivek sir, good evening. This is Rajesh from Megaplast. How are you?
Yeah, I'm fine. Yes, yeah. Sorry, I could not see you. Now you are visible. Please, thank you so much.
Yes, sir. Sir. This is a very interesting aspect, sir, which you have taken on tunnel engineering. But only thing what we are noticing is elsewhere in the world they use only LIDPE, but in India they're still using PVCE.
No, that is not the case. Actually, in the composite material, PVCP is widely used as the base material because PVCP has a very good tensile strength and it permits very high elongation. It is preferred against the low density polyethylenes. And even in the dam engineering, PVCP is the widest used material simply because of its strength, that is the tensile strength and high value of elongation. Even the UV resistance point of view, PVCP is much preferred. But anyway, we use the composite set, not a single material.
But still, I request you, sir, worldwide it is changing. Last a couple of maybe 10 years back, it is all changing to white color LDPE. We can submit samples to you. You can check it in any lab, sir. We can submit our
no matter.
LDPE,
No matter. We are open actually. See, Mr. Rajesh, what I mean to say, materials are always change with the passage of time. There are newer and newer inventions in every material. My focus today is to underline the fact that different kinds of geosynthetics are used. Their functionalities are more important than what material you use. For the filtration purpose, you use some material. For the drainage purpose, use some other material. For the tensile strength, you have some other choices. But anyway, they are geosynthetics. So my focus is on the geosynthetics. There may be several materials within the geosynthetic class.
Very true, sir. But we are open to submit our samples wherever you want. Wherever
you are most welcome. You are most welcome. You are most welcome. You know, after all, I am a learner. I am a student throughout my life.
No, sir. It's our pleasure, sir, for you to teach us these subjects. It's a pleasure.
You please send me. I shall be grateful.
Thank you, sir.
Good evening, sir. This is Dr. Jayalakshmi from NIT Trichy. I have learned an insight into how the seismic load on tunnel linings are happening. Like you had told, like tunnels in folded rocks, if we have primary waves, it induces compression. and shear waves axial bending, but Rayleigh waves overlaying. Like how far is the instrumentation part regarding how to detect all these things?
Yes, actually, instrumentation is a very exclusive subject in the tunnel engineering. But usually in the rock mass, in the surrounding of the channel, we have to embed the instruments to record the behavior and intensity of the earthquake, to classify the waves of the earthquake at a particular location. And we have to keep a constant eye on the happenings in the surrounding of the rock mass. Because the cost of a tunnel is too big, and the serviceability is also a matter of great concern for all of us, we have to be actively involved in the observations of all these earthquake related movements. Or even without earthquake, there could be environmental changes in the surrounding rock mass, and they could initiate some kind of movements. So for all that, instrumentation has to be done in the surrounding of the rock mass, and that is how we have to keep gathering all the information, understanding it, analyzing it. And that is also a separate subject as to what kind of instruments to be embedded in what kind of situation. But that is also very interesting.
Yeah, right. Thank you, sir. Thank you so much.
Any other question from the participants, please?
Hello, good afternoon, sir.
Please.
Yeah, we are looking at geosynthetic as a permeable membrane
Uh-huh.
to prevent, as a non-pervious membrane to prevent seepage. Can the synthetic membrane be used for improving the soil bearing capacity? Yeah, that's it.
Yeah, sure. So, actually speaking, when we say membrane, the phraseology itself defines that there should not be any kind of permeability into the material. That is, no access to water to go across, and then it is called a membrane. If you allow the water across the plane, then it is called filtration. So when we use the property of a membrane, we try to ensure that permeability is very, very low, maybe in 10 raised to minus 2 centimeter per second or so. That is how the levels are. For the filtration purpose, we have to design the permeability. Okay, this material is designed to permeate liquid with so and so viscosity with this rate. Then it is called a filtration property, design filtration property. So that is called the geo filters. Your second question, soil bearing capacity enhancement. Usually when we use the basal reinforcement, we don't improve the bearing capacity of the soil. Rather, we improve the behavior of the soil and we reduce the settlement in the foundation. See, the difference is very subtle. Improving the soil bearing capacity means changing the quality of the soil, and soil itself will be bearing more and more load. Whereas here, by way of reinforcing the soil, we are allowing more load, greater load with lesser deformation in the soil, lesser settlement in the soil, lesser subsidence in the soil. So we call it geo reinforcement or the basal reinforcement in the ground. So performance of the soil is improved. And in the parlance language, people say that soil bearing capacity has been improved. But technically, it is not improvement of the soil bearing capacity. It is improvement of the soil behavior under certain loading condition. So I think I have answered your question.
Thank you so much.
Please.
Can we move to the next question, please?
Or, you know, my chat box is open. You can type in the chat box and I shall read the question.
So good afternoon, sir. I have one more question.
Please, please, please.
Like you have told about the long-term effects, right? Like creep and other things. Like most probably you might be using the creep value of 4 or something, including the biological damage, chemical damage, and other things. But if creep like evaluation, like for that, what are the steps involved, and how do you overcome that in the design? Because design might be costing more if the creep effects are not taken into consideration properly. So, do you have any comments on this side, sir?
Yeah, actually, your observation is very valid, and it is not limited to the tunnel lining design, but that applies to all the structural elements, be it the T-beam bridge or the, you know, the pre-stressed bridge or any kind of, you know, the um, two-way slabs or whatever structures. But the creep, you know, that is the most important factor that we need to consider in the design. So, you know, there are different design philosophies by which we do address the issue of the creep. You know that in the original design philosophy of the ultimate load, in the ultimate load theory, you know, we used to put all together the strength of the material and the creep and everything, and whatever was, you know, the maximum result oriented aspect was taken as the ultimate load. And that is how, you know, the ultimate load theory used to work in the olden days. Then we came to the working stress method and we applied, you know, extraordinary kind of a concept called factor of safety. In the factor of safety, we duly considered the effect of the creep and everything, and accordingly we derived that in so and so application, the factor of safety for concrete should be these, factor of safety for the steel should be these. But the creep was conceptually embedded into those calculations, and then we came out with the heuristics that okay, this kind of factor of safety will be considered in the working stress design. And then, you know, we went ahead to go for a limit state design, and in the limit state design, we went for a probabilistic approach that these are the percentage of failure, and we combined it with the you know, the deterministic approach of the factor of safety as well. So in the probabilistic theory called the limit state, we make combination of the two, factor of safety as well as the percentage of failure or the probability of the failure. And that is how we developed our concept of the creep. And if you recollect, there was a concept in between that is called the crack section design, in which the crack width was actually computed by estimating the creep and all. So there are different theories to compute the creep. But anyway, in whatever theory you use for the particular design, you must consider the creep. If you don't consider the creep, then either your structure will be under safe or you will be overestimating the factor of safety and you will go for a very costly design. So usually it happens that creep becomes very dominant aspect of the design. And if you design with the consideration and computation of the creep, that I'm sure that your structure will be long lasting. And the creep also, short-term creep and the long-term creep, both the considerations are required to be done. And that is how we can design, you know, long-lasting structures.
Right, sir. Thank you very much, sir.
Very pertinent question. Thank you.
Can I have one query,
Please,
Mr. Kapadia?
please, please.
When you have this membrane between the permanent lining and the above the permanent lining, then there is an interaction between the rock mass and the lining. So how does this geosynthetic layer or membranes, whatever we are using there, how do they interact, and means what is the impact of putting these there? Okay, they will be providing filtration or permeability.
Sir, got
Yeah.
your question. you might have seen my slide showing fastening mechanism.
Mhm.
There was exclusive slide on the fastening mechanism.
Yeah, yeah.
So, the fibercrete that is in the contact with the rock mass and the geosynthetic material, they are fastened in such a manner that the strain in both the material will be the same. And by keeping the same strain, we are allowing the stress interaction in entire cross section. The
Okay.
primary lining, the geocomposites in multiple layers, and the overtop concrete lining. So all the material behave as a composite.
Okay.
And that is how we do the design. So that is called, sir, constant strain problem.
So
that is called
this
constant strain problem.
strain will be same, the stresses will be different there in different material.
True, sir. Very true, sir. Very true, sir. And accordingly, we do the design.
Okay, okay. Oh, thank you very much.
Pleasure, sir. Pleasure.
Do we have any further question, please?
Yeah, just one more thing, Kapadia.
Please.
Means are there analysis using the dynamic loads also? Like initially you said that we can do this or that, but do they generally do this dynamic analysis also?
Actually speaking, sir, when we design a large section of the tunnel, in the olden days, they used to go for only pseudostatic analysis.
You have to mute some.
May I request others to kindly mute their mics, please? Sir, actually, in the olden days, we used to go for the pseudostatic analysis. But nowadays, we have the finite element softwares and, the Plexis kind of softwares. So we model the entire rock mass in the surrounding of the tunnel for significant cross-sectional area, and different sections are given to the FE analysis. And we really go for the dynamic analysis, and that too from time to time the same model is rerun. We do the instrumentation in the surrounding rock mass. We give the values of the movements of the rock mass, and accordingly we go for even backward analysis. That is called the behavioral understanding of the movements in the rock mass, and then we estimate the creep factor and the sliding factor of the rock and the strains in the rock mass, and accordingly we estimate the repair measures as to when they will be taken up. And that is how we take the planned closure sometime if the strain is requiring some kind of intervention. So nowadays the dynamic analysis has come into vogue, and it is widely accepted kind of an exercise.
Okay. Thank you very much.
Can I have one question?
Please,
Myself,
please,
Dr. Sanjay
please.
Burele. Yeah,
Please,
myself, Dr. Sanjay Burele from CWPRS Pune. You have shown one slide regarding that at the toe of the hill, one canal you have shown, and where you have
Yes.
provided filter.
Yes.
Sir, I want this thing depend on the area, sir. Actually, I have done some studies in Konkan area, sir. There was canal going on. Actually, what happened in Konkan area? It's a complete laterite soil, sir. And what happened? The seepage takes place in the laterite soil, and when it goes and seep and at the face of the rock, it starts flowing, and from the bottom, from the bottom of the canal, it fails, not on the side of the canal, sir. So this type. So we were thinking about that also, sir. You have shown that, but it doesn't work. It works on particular area, sir.
No, not area. Actually, the loading condition and the drainage condition. These are the two critical things to be understood. So every application will have its own kind of a solution. It is not that one measure fit all kind of a solution that the geosynthetics can provide you. it is one of the solutions, and there could be different versions of application of this geosynthetics to work out a proper solution. So every problem is a unique problem, and we need to understand the grassroots level reason of the problem, and then we can find out the solution thereof. So one solution cannot be fitted everywhere in the world. So you have rightly observed that it situational solution. There can never be a generic solution.
Yes, sir. Sir, there what happened, sir? They have means there is a it's that study was done by irrigation department of that Konkan area, and there is a design unit also, CDO design unit in Nasik. They have suggested lot of measures, sir. All the measures were failed, sir. There, and we have given one simple solution. That is only piles has provided, sir, and it is stopped, sir.
So what I mean to say, there could be different solutions, but all the time, it is not that very complex solutions is required. Sometimes very simple solution can work very effectively, very cost effectively.
Yes, sir.
So, it is not that very complex solution is considered a smart solution. Smart solution can be very simple, very cost effective even. So, and that is, that is called the engineering. Engineering is not making the things complex. Engineering means understanding the nature and accommodating with the rules of the nature, finding out the best, simplest solutions in the world. That is called engineering.
Yes, thank you, sir. Thank you. Your presentation was nice, sir. Very good, very nice. It was really means we have seen new things, sir. Yes, sir. Thank you, sir.
So much. Thank you.
I guess now it's time to conclude the session. Thank you to the speaker and the participants for the interactive and lively question answer session. My thanks are due to Professor Mahinder Singh for giving the brief about ISRM India activities and also introducing our resource speaker. I would like to convey my special thanks to Vivek Kapadia ji for sparing his valuable time for conducting this virtual training session. Thank you. Stay safe, stay healthy. Goodbye.
Thank you very much. Okay, Vivek ji.
Thank you so much. Thank you so much, sir. Thank you so much to all.
Okay, bye.